welcome to our series of complimentary webinars. Today we're going to be talking about CDM controls in manufacturing. And as many of you may know, none of the industry standards adequately cover these issues. HPM is covered well, but CDM is only partially covered by these industry standards. And today we're going to share with you a set of techniques that will allow you to develop a better understanding of the technology and how to implement these controls in your facilities and to enhance the experience that you'll have controlling CDM damage. We will also cover the areas of CDM controls that are missing from the industry standards. Rules of engagement are that all of your phone lines are muted, and yet we want you to ask questions. And there are two approaches. One is to use the webinar dialog box to send a question, and the other is to verbally ask. And in order to do that, you can go to the same webinar box, raise your hand, and we'll respond by unmuting your line and be able to talk with you. This session is being recorded and will be available next week. Regarding upcoming events, we have our annual 4-day workshop here at headquarters in July 21st to 24th. And this year we're especially excited because it's become an international event. We have attendees coming from China, Taiwan, Chile, Mexico, and of course the United States. And during this session, we will be introducing several new class exercises where you actually get to test and measure important issues along with new topics, and we hope to see you there. Now, many of you have heard of the winter that we had here. It was unbelievable. I can't say it any more clearly than that, as these images show you. The amount of snow that we got was extending over the first story of the house, and really quite an exciting year of snow. Now, this time of year, things look a lot better. This is the view from the classroom, and as you can see, a lot more pleasant. We're going to cover these topics, and we'll be, again, willing to and interested in taking questions as we go. So don't hesitate to let us know. Thank you. There are a few terms that I'd like to show you so that you'll be familiar with them when we present them later on. I expect most of them are familiar to you. Charge board event may not be this close cousin to the charge device model, as is CDE, or the cable discharge event. The stress characteristics to the product all have that very fast rise time in picoseconds, resulting in a damage that is CDM in nature to varying energy levels. And then, of course, electrical overstress, which is over voltage or current to the device. We think of ESD as a subset of electrical overstress. And then we'll be using the term class 0. And here you'll see when we use that term, we're referring to devices with thresholds less than 250 volts for either HPM or CDM. And this includes the new categories established by the ESD Association, Class 0B and 0A, which, as you can see here, are sub-levels of the 250 volt entry point for Class 0. We have also seen the need for an additional category that we call Class 0, 000, and this is for the extreme sensitivities of components that are less than 50 volts for either HBM or CDM. Do everything you can to avoid these categories. It is particularly challenging and warrants great care, and again, great care in trying to avoid it with your design team. Now, what would you estimate the failure rates to be in comparison? This is across the industry, and it's based on input from many credible sources, such as the Industry Council and failure analysis experts from IC suppliers. So what would you think is the relative occurrence of failures between CDM and HBM? Well, it turns out that CDM dominates the failure mechanism and has for some time. This figure of 99.9% includes the charge board event and cable discharge event because the characteristics are so similar, except for the energy levels being much higher for the charge board event and cable discharge event. So HBM failures, there isn't much room left for them, and it is interesting that some of the failure analysis labs report that they have not seen an HBM failure in their FA labs in over 3 years. A few initial thoughts of a high-level nature. To implement a CDM in your program, it's critically important to have sound requirements. And for CDM, they almost invariably require some level of customization. And as we said earlier, industry standards do not adequately provide that information. A full understanding of the technology of CDM is essential. You need to develop your own subject matter expert in-house or within the corporation to guide these practices. Manufacturing must require the sensitivity data. I say it this way because of my own personal experience managing AT&T's program. We found that as skilled as the design team is and was, there was no focus on the ESD end of things. So we, on the manufacturing side, had to make it a requirement prior to the introduction of new products. This has become especially important for the extreme sensitivities of Class 0. Don't wait for your design team to take the initiative. Do it yourselves. And unfortunately, IC suppliers generally don't publish the CDM data, which is particularly frustrating. So when you go after it, you'll find it's not in the data sheets and difficult to locate. If you ask for the JEDEC qualification report, it is there and required for JEDEC qualified devices. So that often makes it a little easier to obtain the data. And I can't emphasize enough the importance of a robust compliance verification strategy. That topic goes beyond the scope of this webinar, but it is fundamentally essential and expands the checklist considerably. Here is a chart that offers objective evidence of the importance of adding these CDM controls to your program. In this time frame on the left, you'll see that this company had good a good S2020 program in place, and yet they still had high yield losses, as high as 22%. In this time period, at week 45, they introduced an aggressive charge device model, cable discharge, and charge board event set of practices and controls. And the result was over initial weeks, very short period of time, a significant improvement in the defect levels, and as they continued improving their performance, almost 100% yields, even though these were Class 0 devices. Again, this is objective evidence that the controls we're about to discuss are essential and fundamentally important to protect your products, not only internally, but from reliability issues. As a brief review of the two models, this is the human body model, and it simulates a person becoming charged and discharging to your product, as you'll see here. In this simulation, the component is grounded, and that is one of the requirements within the standard, and it enables repeatable test results and worst-case conditions, which means in normal practice, if you were to stress a device that is not grounded, the HBM failure level would be appreciably higher than the test results from the industry standard tests, which is one of the reasons that we see less human body model failures. But the other is that most companies are doing an excellent job grounding people. And once you've done that, you have eliminated the human body model as a risk. So it makes sense that there are very few HBM failures today. This sketch or schematic at the bottom illustrates the concept of the person becoming charged and the charge flow going from the person to and through the device to ground. This is the charge device model, and it is what it sounds like. It replicates the device becoming charged and then discharging to a conductive surface, as you'll see in this animation. Here the device is sliding out of a shipping tube, and in the process of sliding out of the tube, it became charged, then landed on a conductive surface. And that, simply put, is the charge device model. Now, it is schematically represented here, where we show the capacitance of the device, which is an important variable, because the size of the package governs its effective capacitance, and also the amount of charge that can be stored in the device. So therefore, a larger device is able to store more charge and is more likely, not necessarily, but more likely to have lower charge device model failure levels. In other words, they would be at greater risk at lower levels of damage due to CDM stresses. Again, because of the greater capacitance, higher charge level, and stronger discharge currents. In this case, the flow is from the device through a contact resistance to ground. This contact resistance we'll discuss in more detail, but it is an excellent opportunity to prevent CDM damage. And again, as a reminder, the reports that we're getting across the industry are that 99% or greater than 99% of ESD failures today are CDM in nature, including the charge forward event and cable discharge. It's important to understand that ESD is a two-step process. Sealed by itself does not cause damage. What it requires is for the product or the item to become charged. And in this illustration, we're looking at an insulator that charged by frictional action the conductor, which could be your component. That does not cause the damage. What does cause the damage is step 2, where the device is then grounded, or contact is made to another conductor at a different potential. We refer to this as metal-to-metal contact. So when that occurs, the charge is swiftly removed. In fact, the entire transient is 1 nanosecond with rise times in tens of picoseconds. And summarize it, ESD is the sudden transfer of charge between objects at different potentials, or through an arc or spark just prior to physical contact with your product. Now we're going to talk about countermeasures. And we will discuss both strategies. And here we have that schematic that we saw earlier, the capacitance of the device relative to ground, and its discharge to and through a contact resistance to ground. So what we're trying to do to prevent damage is to reduce the discharge current. Remember, it's not the voltage, it's the current flow that causes damage. So what we're doing here is looking at the two strategies. On the left, we're indicating that if we can lower the device voltage, that will reduce the discharge current. And this strategy is the one that is in the industry standards, such as S2020. The other opportunity is to manage the surface resistance at the immediate point of contact, right here where we're showing it on the schematic. Here's your device, here's the surface. So we're talking about controlling the resistance at this contact point. Both will reduce peak discharge currents and provide protection. On our website, there are a series of educational videos, short vignettes, and this video that we're going to show you, or summarize for you, is video number 11. So you can go there and see the whole thing. And we're comparing discharges from a charged simulator gun, ESD gun, to a pair of tweezers. Here in the video image, you see the gun, and here is a pair of tweezers. The handle of the tweezers is metal and conductive. The tip you'll see is black and static dissipative. Now, a close-up reveals that this is the tip of the gun, and in this image, the gun was set at 17,000 volts. So imagine this tip is your charged component or charged board, and it's approaching a pair of metal tweezers. You can see there's an arc jumping some distance, representing tens of amps and a very strong discharge. Now, when we reposition the charged ESD gun to the dissipative tip of the tweezers, we have an arc that appears here, but it's a very small arc in comparison. It is corona discharge, which is very low energy and non-destructive to even extremely sensitive components. So by simply switching to this static dissipative tipped tweezer, you have built in considerable protection into your program. And again, the material is right at the point of contact where you would be conceivably touching your circuit board or your devices. Now, does voltage kill devices? The answer is no. It's the current transients that damage devices. And it almost always involves conductive contact with another object, tools, automation equipment, various items within the manufacturing environment. And again, we call this metal-to-metal contact at touchdown to imply that that is where your product touched the conductive material. High fields look dangerous, but it requires that step 2 to trigger the damage or to trigger the current flow, current transients, high currents, spikes, resulting in the damage. Now, there are exceptions, 2. Reticles, those are the wafer masks that are the photolithography masks that are used to create the images for wafer pattern generation. Very fine lines and spacings on glass, a perfect insulator or very good insulator, and therefore a field near these reticles is a high risk to them and can cause physical damage to the traces on the mask, resulting in repetitive failures of devices. SAW filters have similar geometries and similar risks, although many of them have designed-in protection to prevent this mechanism. To consider both strategies, one approach for class 0 is, again, the surface resistance. And as you go deeper into the class 0 region, the resistance at the point of contact or at touchdown needs to increase. So to provide better protection and resistance to those high discharge currents. Regarding voltages, the same concept applies. The voltages must be kept lower, again, to prevent discharge currents for these extremely sensitive devices. Because lower voltages will produce currents that are strong enough to damage devices. So for class 0, you need to make sure that the charging levels on the device are below its thresholds, and resistance levels on the materials you choose are high enough to keep the discharge currents below the failure levels. Both strategies are important, and we have found in our work with AT&T and clients since then that surface resistance is actually more cost-effective. One of the reasons is that voltage management becomes extremely difficult for extreme sensitivities. And here we're talking about also the human element. With voltage control techniques, you often use ionizers, you use field meters, and they both have considerable number of pitfalls. In fact, for the field meter, we have a half-day seminar or workshop on the pitfalls for measurements in factories. Many ways for these two approaches to let you down, so to speak. And for class 0, it requires very low voltage management, and it's difficult to consistently implement these controls. So how well can you really control voltage, again, especially for class 0? Well, here's a chart that gives you a sense of our experience with this. If you're dealing with 1,000-volt sensitivities, no problem. As you get down towards the 100-volt area, it becomes increasingly difficult. And of course, when you get down to the level of TMR heads, which, by the way, is at the 1 to 3 volt level, it's impossible to control voltage. It's just not going to work. So that sets the stage for all of these human error difficulties, and also speaks volumes about the importance of using surface resistance as a countermeasure. Field meter pitfalls. We rarely see people using these meters correctly. In fact, none of the sites we have visited to date were using the meters correctly. Some were using them partially correctly, but none fully understood the pitfalls or there's numerous ways you can get misleading results from the meter. Examples are voltage suppression. If you're measuring items while they're sitting on your workbench, you're likely to have faulty, or I should say incorrect, representation of the risk. It would tend to looking like things are much better than they are. One of the reasons for that is that the field of view of the meter is 4 times the measurement distance. And generally, people use meters with a 1-inch measurement distance. So therefore, the field of view is 4 inches. And those measurements take into account anything within that viewing circle. So if you're, again, if you're measuring something on the bench and part of it is the workbench itself, the ground measurement of the bench or the 0 voltage level will lower the reading artificially. Often people measure without grounding the meter, or they use the incorrect measurement distances. And these are a few of many that result in readings that are not accurate. Here's an illustration of the grounds in an automated tool influencing the measurement. Here you have the devices right in this track in the center. And we have this meter that's measuring the area and averaging in all of these grounded metal objects. Therefore, the reading is not indicative of what the component is experiencing. So, simply put, the field meter is the wrong choice for this application. Better choices would be either the electrostatic voltmeter or contact voltmeter. Here's another example. We have, again, the field meter. It's measuring an automated tool, the vibratory bowl feeder, and the reports that we got were that measurements were made at 500 volts by a customer visiting a contract manufacturing site. As a result of this, I was actually flown to Korea to investigate. And having seen this photograph before I got there, I knew it couldn't be at 500 volts. You have the metal of the equipment, which is unavoidably grounded, and therefore the meter, there's no way the meter could have been at 500 volts. Well, it turns out, as we said before, it was the wrong meter, and in this case, it turns out that the engineer from the customer visiting the contract manufacturing site was not grounded. So he and the meter were at 500 volts, not the equipment, and triggered this international event, so to speak. Now, ionization. People tend to think it solves everything. In fact, I was there at one point myself. There's a tendency to think, well, we'll just put an ionizer there. That will take care of it. And again, there are numerous pitfalls. We're going to discuss, a small subset now. But here is an illustration. We have an insulator resting on a grounded work surface, and it's charged on both surfaces. We bring in the ionizer. It floods the surface, the top surface, with ionized air, both positive and negative ions, which recombine on the surface, neutralize that top surface, and the charge is balanced or removed. The bottom surface of the insulator remains charged because the airflow can't get to it. Therefore, it is still charged, and depending on what happens next, able to introduce discharge stresses to your product. Now, if we were to lift the insulator, now the airflow can get to that charged surface and neutralize it as well. So think of an ionizer like a can of spray paint. There's some overspray that will go around the edges perhaps, but you really need direct access for it to be effective. You'll also notice that when it was sitting on the work surface, voltage suppression reduced its efficiency. Looking a little more closely at the resistance strategy, it is significantly less prone to human error. Typically, you put a resistive material in the right location within the process, you solve it once, and move forward with robust protection. And if you pick the right materials, they will perform independently of relative humidity. Therefore, you could eliminate the need for ionization in some cases. There's less maintenance. For instance, the ionizers require regular testing and cleaning and so on. And implemented effectively with robust compliance verification, humidity controls can be greatly reduced, if not eliminated. Continuing with the resistance strategy, the approach is to eliminate all metal contact with the device. That's the objective. Whether the device is grounded or not, we do everything you can to eliminate that metal-to-metal contact. Now, it's not always possible. So what do you do then? Well, what you do is you ground the device safely through a static dissipative material to reduce peak currents, get the product to zero, then you can make direct contact with a conductive, hard-grounded metal object, such as a test set. Bring all of your tools to ground prior to contact. And then verify all of this is working effectively with ESD event detectors. This is a viable strategy to verify initially and also ongoing process management to make sure that your product is not being stressed. And allows you to make continuous measurements while activities are progressing as normal. And again, not emphasize enough the importance of a robust daily compliance verification for these CDM strategies and materials and tools to verify proper tools and those that are being used that come from the approved materials list. Here's a chart that gives us the definitions for materials and the resistance ranges: conductive, dissipative, and insulative. Conductive materials allow the charge to remove too quickly and need to be avoided for CDM purposes. Dissipative materials, that's the sweet spot. You want to be in the dissipative range and ideally more or less in the middle of it. This range that you see here is the definition and is the maximum allowable range. For extreme sensitivities, you want to narrow that range into the sweet spot, which is typically 10 to the 6th to 10 to the 9th. This material property allows you to safely, reliably, and cost-effectively minimize discharge currents and protect your product. And as you know, insulators, static generating, and are very slow to remove charge and therefore leave the device charged, ready for metal-to-metal contact to cause damage. ESD event detection is especially important for the reasons I just outlined. It's a non-disruptive technique that allows you to definitively determine if stress is occurring or not. Here is an oscilloscope image of an ESD event. By the way, scopes are a particularly good tool for measuring ESD events. And this detection strategy is based on the principle that every ESD event triggers an RF transient that can be measured. And it is also a non-contact method for auditing, surveillance, diagnostics, troubleshooting, and process qualification. Very effective tool, and it's non-invasive. It can be done remotely, outside the equipment, without disrupting the product flow. So everything is as normal. The product flow, the rate of flow is the same. There have been no other objects traveling with the product, such as meters, that would alter the effective capacitance of the product. So it gives you a real-world assessment of what's happening. That's the good news. The bad news is that it detects all kinds of RF signals. It can be from light switches, relays, and the like. So you have to learn how to distinguish between transients detected with the event detectors that threaten your product and those that do not. And that's where most people tend to have difficulty. I guess another way of putting it is that event detectors are equally as confounding as they are effective. So it's worth the effort to go through the learning curve. And it is possible to determine with these instruments the actual arrival time, amplitude, and location of events. Here's an illustration of a use of the event detector, and you can see again the details. This is video number 10 on our website, and this was in Malaysia. We went into the room and the meter was going crazy. It was just nonstop. In fact, all of the event detectors were useless. We always bring a variety of detectors with us because each have their own pros and cons, but here they were all useless because there were so many events so rapidly occurring and such strength that the instruments were not able to discern where the sources were coming from. The next day we went in and analyzed one workstation by itself and one by one eliminated the sources. And here is a list of the sources, or the more significant ones. It was incredibly informative, very interesting investigation. Go see the video and you'll see just how rich it was with learning experiences, illustrating the importance of the event detector. Good news. One of the major hurdles has been resolved. Simco Ion has now available an ESD calibration device. This is an ESD simulator. As you can see, it's small, can be placed inside of automated tooling, and can trigger ESD charge device model events at voltages set with a power supply. So it's a really slick instrument that can be used for calibrating your event detectors, both in the lab and in place in automation equipment. Really a great breakthrough. Okay, here's a case study that illustrates the use of these approaches and some of the subtleties that you can run into. You know, people often say, well, you know, when are we going to have a standard for class 0 as an example? I doubt that there's ever going to be a meaningful standard because invariably it requires such customization that it just does not lend itself to standardization. Here's one example. We have a circuit board with a class 000 device on the board and no design transfer information. And as I said earlier, you know, for manufacturing folks, make sure you require that data from your your design team. This example is one of the reasons for doing that. In this case, we had a device with sensitivities of 15 volts for CDM, 10 to 15 volt range, class 000, extremely sensitive, and no idea it was coming. We ended up with 100% failure rates during ramp up of a $1 billion product line. Yes, that's a B for billion-dollar product line. You simply don't want to be in that position. As we were speaking with the executives of AT&T way too often. So, lessons learned. Make sure you get that data from your design team. And in this case, we had to think outside the box. The remedy, again, was customized. We developed, and I'll show you shortly what it is, a custom shunt that was placed on the device and protected it temporarily through most of the manufacturing operation. Prior to that remedy, we tried everything. We had, you name it, we had all of the standard controls in place, and it wasn't sufficient. We still had those 100% excursions and failure rates that were particularly troublesome. And we spent over $300,000 implementing those approaches, and they didn't work. So in the end, we developed this customized shunt. Shunt is here on the left. This is a foam material made of static dissipated material with a surface resistance of 10 to the 5th. It was, as you can see, custom formed for us with a magnet embedded in the lid in this area. Now, on the right is the bottom of the device. What you're looking at is the surface that would be actually on the circuit board. And as you can see, the leads extend out beyond the edge of the device, were visible and available for contact with this dissipative foam. That allowed us right immediately after reflow, solder reflow, to simply place this magnetized foam, or I shouldn't, well, foam with a magnet in it, on the device, which fortuitously had a metal lid that would allow the magnet to hold it in place. So it remained on the circuit board on top of this device until the board reached the test sets where it was removed, and of course removed for shipment. Now, that gave us almost 100% yields immediately, whereas the standard countermeasures did not work. It took time, but our Bell Laboratories team went back, redesigned the device, and made it much more robust at 100 volts. It got us out of that class 000 region and made management of the process much more practical and viable. Here's an example of trays. This is what we think of as a pending problem. Typically, these JEDEC waffle trays have very poor control of the surface resistance. We see on the same tray areas where it's an insulator with 142 volts on it, or some voltage. In the other areas of the same tray, it's too conductive. In this case, on the right, it's 10 to the 3rd ohms, which is below the dissipative range. Over here, it's 10 to the 12th, which is above the dissipative range, on the same tray. Very common scenario. Here's another example of the difficulties with automation and the need for customization. This investigation was initiated because the customer required the contract manufacturer to certify that their equipment would safely handle and process components that were 50 volts or higher, CDM. So they wanted 50-volt certification of the process. Here in this particular stage, we found that the devices were charged to 200 volts, which violates the customer requirement at face value, or as it might appear. But it turns out that even though the device was charged to 200 volts, damage was not occurring, and we determined that with the use of the event detector. Here we placed the event detector strategically immediately adjacent to where the product was being processed at that 200 volt reading. And it turns out that with the event detector set to a sensitivity of 10 volts, that no events were happening. So we know that no stresses at or above 10 volts were occurring, which was a significant safety margin well below the 50 volts, and therefore not an issue. Now, you can also leave the equipment installed and monitor it automatically so that going forward you can know with certainty that no discharges have occurred to your product and therefore certify your process. Now, another tool in the process is shown here. In this case, the potential on the device was 30 volts. However, to make that measurement, we had to momentarily stop the equipment, which meant it was not indicative of the potentials at normal operating speeds, or it may not have been. So 30 volts was pretty close. It was close to the 50 volt level, and therefore we dug more deeply to evaluate the risk using event detectors. In this image, you can see that we have the event detector here in front. This is a different type of event detector. The antenna is out here, right next to the stage where we saw the events occurring with the use of the event detector. And watching with the negative eye, the equipment was moving so quickly, it was not possible to determine if the discharge was occurring at the precise moment of touchdown or not. So to determine that, we recorded this measurement with a video camera. That enabled us to look at it frame by frame and ultimately determine that there was no risk. The discharge was happening at a moment in time slightly after the device experienced touchdown in this stage in the tool. So we were able to vindicate and certify the tool as safe for 50 volt devices. Here's another example, surface mount tools. Often we find events occurring at surface mount tools, and that requires deep analysis to locate and remedy the scenario. This is one typical example. Now we're using a surface resistance probe to measure the properties of the rubber pickup nozzle that's used for picking up and transferring components. In this case, it was too conductive at 10 to the second ohms, below the dissipative range. Here's another common scenario. During surface mount operations, there are components placed that are not ESD sensitive. They typically arrive in packaging that is static generating. Therefore, it's possible for the devices in that configuration to become charged. And depending on the nature and properties of the pickup nozzle, that charge can be retained, and then when the component is placed on the board, trigger a discharge. We saw this happening in one factory that was resulting in 45% failure rates of circuit boards. Here's a subtlety where the carrier tape on carrier and cover tape was too conductive. It was below the dissipative range. Glove boxes, very common scenario. The glove material typically is static generating, and just the most slight maneuvering of tweezers, tools inside the chamber charges them, resulting in discharges to product and damage. Here's a very interesting case study. This is on an MR head, and it's class 0, and particularly interesting, and again illustrates the importance of customization. The setting of in-process requirements requires first to understand the device sensitivity. We knew up front that the CDM withstand voltage was 60 volts. We did not know what the associated discharge current was. So we had the test redone, recorded the discharge current at destruction, and found it to be 100 milliamps. So as we considered this scenario, we said, let's introduce a 10-to-1 engineering safety margin. So we artificially set requirements for all operations in this facility to a new specification that required a limit for the current and voltage of 1/10 of this failure level, of these failure levels. So therefore, we were dealing with a maximum discharge current transient of 10 milliamps and no ESD events in excess of 6 volts. Now, this 6-volt number is one that you have to develop through characterizing your event detector with each process step. You have to make your own calibration curves by setting the voltage of your device or charging your device to known voltages, discharging it, and characterizing the response of your event detector. The more advanced instruments used for this case study are the current probe that you see here. It's a CT6 current probe or it's a Tektronix product, and it allows you to measure the discharge currents. Here you have the CT6 probe itself and a wire passing through it. So the coil associated with the probe senses the magnetic field and gives you an indirect measurement of the current flow. Then we have the event detector, of course. Now here is there are several aspects to this analysis, but here we have one of the critical test fixtures. And you can see, it's hard to see, but right here is the electrical contact test socket where the product is going to be plugged into. It's a flex connector that connects right here. And what we found, and you'll see in upcoming charts, is that the discharge levels here were too high. And to reduce that, we installed this static dissipative mat in this location and grounded it immediately adjacent to the connector at the same elevation. Why is it at the same elevation? Because of the formula you may recall, the charge Q equals capacitance times voltage. And the capacitance of your device is governed in part by its distance relative to ground. So therefore, if you change the elevation of the device, you will change its capacitance and therefore the voltage and therefore the stress. And the other scenario is to do the discharging as close to the test connector as possible to minimize movement and recharging. So it all makes sense to put this connection or this display pad here. What was surprising is that we had to wait 4 seconds for the charge removal. anything less than that would enable some residual charge to remain on the device. So it required a full 4 seconds to fully remove the charge from the product before you could put it into the connector safely. In fact, this brought the yields back to 100% and close to it at this test set. And later, operators started cutting corners a little bit, not waiting the full 4 seconds. Failure rates started to creep back into the process, and that's when a formal special operating procedure was put in place to guarantee that 4 seconds took place. Here is the measurement technique. You see, here's the current probe, the wire coming through the probe and enabling contact with specific pins and the resulting response. Here's the before and after data. Before and the milliamp measurements on these 3 test sets, all of the same nature. And you can see before the modifications, the discharge currents were in excess of the failure level of the product, the 60 milliamps. Afterwards, they were well below, in fact, way beyond the safety margin we had set. So this accounted for or confirmed the reasons for the dramatic yield improvements. Here is an image captured of the event detection, and you can see that these spikes represent the discharges, and you can see that discharges are still happening, but they're well below the engineering safety margin of 6 volts, as indicated in the prior chart, and certainly well below the failure threshold of 60 volts. So it provides more than ample safety margin. The operation required several metal tools, and due to the fine geometry, it was difficult to switch to dissipative tip tools. So therefore, additional work had to be done to guarantee on a day-to-day basis, day in and day out, again, the compliance verification being so important, to guarantee that the product was not charged and the metal tools were not charged. This was done safely, and these operations were certified as event-free as a result. The bottom line is that that chart I showed you earlier confirmed that those, and again, those are examples of what was done, not the full extent, but those types of process improvements almost eliminated the ESD defects from the process. Now, it took time because there was a great deal of detail, tool by tool, step by step. But over the course of a year, the yields approached 100% with class 000 devices, by the way, at the end of that time period. So all very successful and conclusive evidence of the importance of expanding your CDM controls to include the strategies that we've discussed today. And I want to thank you. I've enjoyed having you with us and look forward to seeing you at our next webinar.